very exciting workshop, I suppose. So I'm going to talk about this law of iterative logarithms of the KPZ equation, and this is a joint work with one of my advisor's excellent graduate students, Shayan Dash from Columbia University. And so I'll just briefly mention what you would expect out of this talk. So KPZ equation, I'm going to say a little bit on this in my first slide. And the law of iterative logarithms, we are all familiar of this term in the context of Brownian motion. So I'll try to sort of bring in this law of iterative logarithm for the Brownian motion, try to compare that with the KPZ equation, and at the end probably would sort of give you some idea about the proof techniques and like the tools that we use. Okay, so let me just start. Let me just start with saying a little bit on this KPZ equation. So this is like a KPZ is the abbreviation of this three names, Carter, Parsi, and John. So these are like three physicists. So they were investigating one of these popular random growth models, ballistic deposition models. And they came up with this nice stochastic partial differential equation, which became this canonical stochastic PDE for like this all the other kind of random growth models or the interacting particle systems. So that's sort of like one of the major motivation for studying this stochastic PDE. And so this this PD, like this is the solution of this stochastic PD is like a height function, and this is like has two variables, t and x. So so here you can see this stochastic PD. So on the left hand side there is this time derivative of the height function, and on the right hand side there is this three terms. So there is this, the last term on the right-hand side is this white noise, which is sort of like giving a force at independent force at every space-time location, and the first term on the right-hand side is this is this like a Laplacian term, which is sort of smoothing the solution. And the most important term is this lateral growth term, which is like this quadratic nonlinearity in the stochastic PDE. And this is sort of like coming because like in any sort of growth models, what happens is that like if you consider time increments of the height in time, then there is a component which is coming from the slope of the curve. And so that could be a complicated function of the slope. But the part, if you take this Taylor expansion of any complicated function, the part which would be sort of like dominating in terms of like taking the macroscopic limit is this quadratic nonlinearity term. So that in that way, it's like sort of like the most important term, and that brings in like this stochastic PDE, and it became like a canonical stochastic PDE for the models for this large class of random growth models. So here you can see that there is this nice picture. I took it from like internet. So this is a picture of like a fire, and the fire is going through, sweeping through like this white region. So this is not like snow or something. This is like supposedly this is like some films of the seeds falling from the trees, and this fire is sweeping through that. And what is sort of very interesting is that whilst doing this is forming a surface which is like very reminiscent of like the KPZ font, or the font that one would observe in most of this random growth models modeled through like this Carter-Parsi-Young equation. So this shape is interesting for like in another respect is that you can sort of like see a inverted parabolic structure, and it's going to sort of come in my next slide as well, like how this inverted parabolic structure appears in the solution of this stochastic PDE. So let me just go to my next slides where I sort of describe in details like this solution theory and like the motivation for our problem. So, so one of the interesting thing about this Carter-Parisi-Young equation is this presence of this nonlinearity term, which makes it a ill-posed stochastic PDE. And there is like a lot of attempts to make a rigorous solution, a rigorous understanding of this stochastic PDE. I will not go into the details of the story, but what became the physically relevant solution of this Carter-Parisi-Young equation is this thing coming from this another important stochastic PDE called stochastic heat equation. And this has this very simple structure. So what turns out, and it's like sort of came out in the seminal paper by Bartini and Gibbs, that if you take the log of the stochastic solution of the stochastic heat equation, the solution of stochastic heat equation has like a profound solution theory, so we can make sense of the solution and log of it when we start the stochastic heat equation from a positive initial data. So the log of the solution of the stochastic heat equation is the physically relevant solution of the KPZ equation, which is also called as like Kohl-Hopf solution. And our whole sort of like investigation would be centered around like this Kohl-Hopf solution. In particular, we would be interested in like studying this Kohl-Hopf solution when the initial data for the stochastic heat equation is the delta initial data. And that we call that as a narrow corresponding solution of the KPZ equation as the narrowest solution. And that's why like you can see I made this notation H and W, and W stands for the narrow H. There is this interesting work came in like almost 10 years ago in the work of Americorwin and Postel, so who showed that this narrow solution up to centering and scaling converge to the Tracy-Widom distribution, which is a distribution coming from the random matrix theory, minus a parabola. And this sort of, you can think of it as any spatial point. This is this our KPZ height function up to centering and scaling is almost would look like a random shift plus in the inverted parabola. So that's explained the sort of the inverted, this parabolic sort of shape that I showed in the my previous slide, and also sort of gives an explanation of this physical phenomenon. But what is sort of like we are interested in is that this in this macroscopic limit that Americorwin and Postel proved, how the peaks and valleys of this process for which we are taking this macroscopic limit would behave as t goes to infinity. And this we will answer by law of iterative logarithms. There are other ways to answer it, but for this talk, I'll focus on this law of iterative logarithms. And so as I mentioned, as I promised before, I will try to sort of compare this LIL for this stochastic process, concerned stochastic process here with the Brownian motion. So with that in mind, I'll just go to a sort of simulation, which is done by Sharon Basigan. So what he did is that he simulated Brownian motion, and this is here I kept it here to show you that this Brownian motion, the peaks and valleys, so have like a symmetric structure. So this fluctuation scale is t to the power 1/2, and there is this envelope of the peaks and valleys, which has like extra factor of a log t term, square root log t term. And so we can try to compare this scenario of the Brownian motion with the one coming from this Carter-Parsi-Young equation. So here we did the same thing for this simulate this rescaled height function of the KPZ equation, and so what we observed is that there is an asymmetry in the sort of distribution of the peaks and valleys. So the peaks are more sort of has like a slightly higher boundary, whereas valleys has like slightly like a sort of a less the boundary of the valleys has less width. And that's sort of like what we expect also theoretically, and that's going to come in my next slide. What is the expectation and what can be proved rigorously? So this is a pictorial view. Now we come to the actual result. So again, I would just like bring in this context of the Brownian motion. We know all this nice things. So the Brownian motion, it has this macroscopic limit standard normal distribution. And the tails would behave as like this standard Gaussian tails. Whereas the KPZ, as I told before, that it has this limit. So if I focus on the x equals to 0 spatial point, then it has this limit, some scalar multiple times this Tracy-Widom GUE distribution. And the tails has like this upper tail has this like specific behavior, which is like would sort of behave as e power minus 4/3 s to the power 3/2. Now, the reason I bring in the tails in this slide, because to sort of like this would give us an idea how to predict what will be the nature of the law of ideal logarithm. So for the Brownian motion, this in the standard Gaussian tails, this red half actually comes as a constant, and this brown 2 here sitting as a like exponent of s would determine this power of the log t term and also the power of this red 2. And the same picture or the same sort of like a rule also applies for this the Lil for the KPZ equation and this lim-sup Lil. So, so there we have to sort of like see what is this constant in front of this h to the power 3/2. So that constant would come as a constant of the inverse of that constant would come as a constant for the Lil, and the exponent of s 3/2 would determine the power of the log t term. So that's how sort of like, that's the prediction we can make. And essentially what we proved is that this would be indeed true that, sorry, this should be lim-sup. So lim-sup of this height function scaled by log t to the power 2/3 actually would be equals to this constant with probability 1. So this is lim-sup, and so that this is sort of like giving us the envelope for the peaks. Now, question is what happens for the valleys? So again, for the valleys, like the tail behavior for the Gaussian, for the Brownian motion is not changing, it's symmetric. So we can expect like a similar thing to happen for the Brownian motion, and exactly same thing happens. Only difference is there is a now for the Layman, the constant has a negative sign, so it should be like sort of since the peaks would be on the downside of the curves. Whereas for the KPZ, since the limit is this Tracy-Widom GUE distribution, and the Tracy-Widom GUE distribution has asymmetric tails. For the lower tail of the Tracy-Widom GUE has actually like this specific behavior, e power minus 1/12 s to the power 3. And again, this constant and the exponent would affect this law of ideal logarithm in the same way as we sort of did in the lim-sup case. So this exponent is going to have sort of inverse of the exponent is going to determine this power of the log t term, and this constant in front of this s cubed term would is going to sort of determine this constants of the Layman. So essentially, that's the expectation, and indeed, what we proved is our sort of result and confirm that prediction. That Layman for this height function scaled by log t 1/3 would be equals to -6 to the power 1/3 with probability 1. So now I'll just come to like very briefly about this proof ideas. So in general, if you want to sort of investigate a lot of particle algorithms, there are two components we need to sort of like make sure that they should be there. One is like this sort of independent structure, at least for the Brownian motion. It's easy to make sure there is an independent structure of the increments. And one has to also be able to control the supremum of the concerned stochastic process and compact sets. So given these two inputs, like one can then sort of like combine those with Borel-Cantelli lemma to get this law of particle logarithm. So this is the rule which has been followed for in most of the stochastic process. But then in the KPZ case, the increments are not independent. So what we were able to sort of like do is that to come up with like two sort of meta theorem, which enables us to sort of like have these two inputs approximate inputs. So our first meta theorem is like this this KPZ height function. So I took it here like the spatial point to be 0. So KPZ height function at T1 is approximately independent of the increment if the other point T2 is a very, very large in comparison to T1. So that's giving us this approximate independent structure. And another thing which became sort of instrumental is this like this increments of the height function is approximately the law of increments is approximately the same as this height function at the difference of the two time points. And so this enables us to control this supremum on the compacts. Of course, like there are a lot of details I'm hiding here, but essentially these are the two meta theorems which are sort of playing the role of these two inputs. And then we can sort of use the Borel-Cantelli to conclude the law of particle logarithms. Now, these are like how one should proceed, but then there are a lot of tools which is like sort of underlying this meta theorem. And as if we have to summarize, we can summarize like those tools through like this three main thing, which are first is this tail probabilities of this KPZ equation. It could be, and there are a lot of things needed for this in terms of tail probabilities, 1-point tails of the supremum of the stochastic process. And it's also like another important thing which became like which played a key role was like KPZ, the tail probability, the KPZ equation at short time. And other thing is spatiotemporal modulus continuity of this KPZ equation, if you think of it as a spatiotemporal process. And the last thing, which is like probably the most important property we needed, is this Gibbs property, which makes us, which enables us to sort of compare the KPZ equation with Brownian motion and derive like nice controls on the whole stochastic process. So these are the three tools, and then combining this, we got this meta theorems, and which makes us to complete this result. So these are the on this proof side what we did, and now I just like finish my talk with saying a bit on like the other result that we proved and future directions which can come up from like this sort of investigations. So, so we also obtained some fractal dimensions for this large peaks and valleys of the KPZ equation, but also result that I mentioned in my slides and which are and the one that I didn't mention was about this narrow age initial data for the KPZ, or in other words, this delta initial data for the stochastic heat equation. So the case of general initial data is still open. Like there are some predictions, but then there are some tool missing there. But there's some progress on the side of parabolic Anderson model, and hopefully one can hope that one can translate that to the KPZ equation. So so these are the two things like probably like are in progress, and are at least actually this first fractal dimension was already there in our paper. But there are a lot of questions which came out from this investigation, which is probably one can be interested in looking at it. So so one of the natural thing is like, how about the fractality of the peaks of the spatial process of the KPZ class model, not the KPZ equation, but like any other models, any other random growth models in the KPZ universality class. And one can ask about the peaks for the spatial process, temporal process, what are the distinction between them, and how to tackle the underlying difficulties there. So then another important thing which came up in like the investigation by other people is this the construction of the KPZ fixed point. So one can ask like what would happen for the KPZ fixed point, like what are the nature of the peaks and valleys for the KPZ fixed point, and is there like for instance Brownian motion has like a short time law of ideal algorithm. So KPZ fixed point being like sort of a universal limit of this random growth models, one can expect to see a short time LIL for the KPZ fixed point, and the question is if there is any idea or any progress can be made along this direction. So these are the things I just wanted to say, and then I'll just stop here, and I'll be happy to take any question.
Okay. Thank you for the talk. So we are slightly late, so maybe if you have some questions, you can just annotate them in the Q&A session, and we can move forward with the other talk, and we will answer the question at the end of the session. So I think now we can go ahead with Busani from University of Bristol to talk about non-existence of bi-infinite polymer Gibbs measure on Z2.
Wait, why am I? Oh, wait. It worked before. So now I noticed that my title is a bit different than what yeah, okay, sorry for that. But that's the one you mentioned is the right one. Okay, so thank you for having me here, and thank you, Alessandro, for the invitation. So I'm going to talk about the joint work with Martin Barrage and Timo Layman. Let me just move this. Wait just a second. Yeah, so there's the story of the last passage population takes place on this on the z-square lattice. So we assign to each vertex a positive weight, so that the weights are exponentially distributed in IID. And then for every 2 points on the lattice, such that one is north and west and north and east to the other, as in the picture with X and Y, then we ask what is the optimal path starting from X, terminating at Y, that it takes only upright steps and collects the most weight. Okay, so what happened here? Okay. So there exists a unique path such as that, and we call it the geodesic, and the total weight that it collects is called the passage time. So this is a geodesic between two fixed points, but then you can ask. Then there's another thing called the infinite geodesics, which is very similar to what you have on metric spaces. So you have an infinite path, an upright path. It could be either rooted at a certain point and sort of going in a certain direction, or it can go in both ways, in both directions, go to infinity. And what it has to satisfy in order to be an infinite geodesic is that for every 2 points on it, the restriction in between the points is a geodesic. And yeah, so when you restrict it, then between it's a geodesic. It turns out that these things actually exist and they're unique. So in the following sense, if you fix a direction between all possible directions, namely between 0 and 90 degrees, then with probability 1 from any point on the lattice, there exists a unique geodesic starting from that point and going in the direction of theta. So the next kind of natural question is, are there bi-infinite geodesics? And the answer is yes. So, for example, a straight line on the lattice is bi-infinite geodesics, because any 2 points you take on a straight line, there's only one way to go from point A to point B, and therefore it's a geodesic, bi-infinite geodesic. And the same thing goes for vertical lines. Okay, so vertical lines and horizontal lines are bi-infinite geodesics. They're somewhat not uninteresting, and we call them trivial. And so we can refine the question to the following one: are there non-trivial bi-infinite geodesics? And here is a very non-exhaustive and well, it's very, very short account of the history of the progress on that specific problem. So the first interest in the problem started from the first passage percolation, which is a close cousin to the last passage percolation, where Layman and Neumann back in the 90s showed that if you, for almost any directions, once you fix it, then there's no bi-infinite geodesic going in that direction. Then this was improved by Alberg and Hoffman, Dameron and Hansen, who showed that it actually holds for every direction. Then moving to last passage percolation, Giorgio, Sulaga, and Sepulveda showed that if you fix the direction, then there's no bi-infinite geodesic for last passage percolation with general weights. Then Basu, Hoffman, and Sly showed the full result for exponential last passage percolation. Shortly after, using different techniques with Timo and Martin, we showed the same result. And later we showed with Timo, we sort of adapted the tools we developed in that work to answer a question, a similar and analogous question to the low gamma polymer. Okay, so I'm going to talk about these two results, the one on the on last passage and the one on the low gamma polymer. Okay, so here I'm going to try to give you a kind of a brief sketch of the proof, which is maybe too much for such a short talk, but okay. So the first thing to do is you can say, well, the whole thing is stationary. So then it's enough to show that there's no bi-infinite geodesic crossing through the origin. And in order to do that, you take a big box of side size n. So the side here, it doesn't say, but the side is of length n. And then you break the all possible directions, the all possible macroscopic directions into batches of n to the 2/3. And so if you show that the probability of going for geodesic associated with a certain batch of direction going through the origin is of order a little of n to the minus 1/3, then using union bound you can sort of make sure that no direction is possible. So the next thing we do is we translate the problem into a question about random walks. So basically you think of the geodesic going from the lower left corner to the upper right corner has to sort of pick an edge where it crosses above or below the origin. And this edge you can relate it to a passage time. And so you could sort of compare those passage time to the one at the origin And this sort of creates these steps of random walk. So you have a random walk going upward or going downward, and yeah, depending whether the geodesic crosses above or below the origin. Okay, so basically it looks like this. You have, if you go upward, then you have this random walk of passage times, and if you go below below the origin, then it's a you have another random walk of passage times. And the point is that that if one of these random walks attain a positive value, then the geodesic would rather cross there than staying at the origin. Okay, so it boils down to a question of do these random walks have a positive maximum? And the way you go about it, so this is the third part, is you sort of kind of tuck under these two random walks another two random walks called S, here it's S down and S up, which we understand very well. They're related to something called the Boozman process. And using these sort of relatively new results about this joint distribution of the Boozman process, we're able to get these the bound of O to the little o of n to the minus 1/3. Okay. Okay. So moving next to the polymers. So if before we sort of for the last passage, what we do is for fixed realization we sort of concentrate on the specific path that maximizes the passage time. We don't care about the rest of the paths. So for the polymer, what you do is you sort of divide your attention and sort of divide your the total present representation of the different paths according to their weight. So a path that collects a lot of weight will be better represented compared to a path with less weight. And the way you do it is you through the Gibbs measure. So you collect all the weights from all the paths, and you just take you just give each path a probability that is essentially its weight, the path of the weight divided by the total weight, which is also called the partition function. Okay, so in other words, when you fix a realization, instead of looking at one path, you're looking at kind of a distribution of paths. And so this sort of kind of it's supposed to summarize what I've been saying. So for last passage percolation, we have the passage time, okay, which is just the weight collected between 2 points. For the polymer, this is just the free energy. For the path that maximizes the weight for last passage is the geodesic, given here, and for the polymer, this is a distribution of paths. Okay, so this is the sort of a knowledge you should have in mind. So this was kind of I didn't require anything on the weights, right? This was seemingly general weights, but in fact, as we required for last passage percolation for the weights to be exponential. So that wasn't an accident. That was that was because exponential last passage percolation is what we call an exactly solvable model, namely that you can explicitly get the first and second fluctuations of the model. Okay, so the analogy in the polymer is what we call the low gamma polymer, where the weights of the distributions are the inverse gamma distributions. Okay. So I'm going to focus now on polymers that have this distribution of weights. Okay, so before we said for the last passage percolation, we said, well, we had these. The main result was about infinite geodesics, right? So here we should sort of explain what's the analogy in polymers. So for the polymers, this is going to be a distribution. So for every realization, you're going to have a distribution on infinite paths. Okay, so these paths can be rooted, such as this one on the left, and it could be, or it could be just unrooted, just going to infinity on both sides. Okay. But similar to the to the geodesics, where we sort of impose the condition on a path to be a geodesic, then here we also have to impose something. So so these are called Gibbs measures, those distributions on the infinite paths, okay, and infinite or bi-infinite Gibbs measures. And the requirement, the condition on being such is the following: if you take a strip, such as in the picture, and you condition on the behavior of the polymer outside the strip, then in between the strip it has to be it has to have the same distribution as your annealed as your quenched polymer between the points, between the endpoints x and y, okay, between the endpoints on the boundary of the strip. Okay, and here's the main result. So for the low gamma polymer with probability 1, every bi-infinite Gibbs measure is supported on straight lines. So this is an analogy to the last passage calculation, where the bi-infinite paths had to be straight lines. Okay? Thank you very much.
Thank you, Ofer. So if there are some questions, then we have a couple of minutes to.
I went too fast.
No, it's fine. It was perfect. We had it was 15 minutes sharp. Okay, let me see if there is not even from the panelists. So if there is no question, I will ask you. Can you just explain with a few more words the comparison part for the LPP?
The what? The
comparison argument.
So I should have. Okay, maybe we can share again. Where is it? Yeah. Wait. This thing here?
Yes, I mean, yeah, you rephrase it as in terms of a random walk.
So these are random walks that are sort of coming from the geodesic, and we don't really. This is basically like in the limit, behaves like this, the area 2 process, if you will. And basically what we want to say is that we can sort of find two dominated Brownian motion. So if you give a Brownian motion a bit of a drift, then it would be dominated by this area 2 process. This is when you sort of go to the limit. We're not using that explicitly. We're using something else. But this is basically the idea. The idea is that the profile of the polymer can be sort of controlled by these, can sort of dominate Brownian motions with the drift. The
limits of these Boltzmann processes that you mentioned. This
what?
So this is the limit of these two processes that you have here in.
So S down and S up, they converge to a Brownian motion with a negative drift.
Okay.
Yeah. And so one of the main points is to use this sort of this independent structure of this of the joint distribution of the Boltzmann functions to get this to get the right bound, to get these n to the -1/3.
Okay. Okay, thank you. Okay, so now with perfect timing, let's go ahead. And so now we have Leonardo De Carlo from Scuola Normale Superiore di Pisa, who will talk about mass transport in models with verticity. If you can share the screen. Is there a problem? We can hear you. Leonardo, can you unmute your...
Okay, yes, I
Okay,
forgot.
now we can hear.
Desktop 2. Okay. Okay, it is fine. Is it fine?
Yes, yes, we can see.
Okay. All right. Oh, okay. So 15 minutes, right? Yes.
Yes.
Okay. So, okay, we'll talk about the mass transport in model with the verticity. So first I will recall some previous work for someone that was already present, but I needed to do that. And then these results come from collaboration with Davide Gabrielli, Patrizia Gonsalves, and Alessandro Arcelli.
Leonardo, before you continue, can you move the bar up because it covers part of the slide?
This bar.
Can you maybe you can do like a whole thing for the whole, so it goes on the whole screen, like a full screen. Yeah. Yeah.
Okay.
Right.
Thank you. You unmuted yourself again. You muted yourself again, please.
Okay.
Okay, good. Okay, so
Okay, I think it did it by itself. So I would say the first, okay, I want to say that I'm considering an exclusion process with a periodic boundary condition. So on the lattice of mesh 1, and with a reversible grand canonical measure, nu rho, that will be parameterized by density rho. So and then okay, with I denote with the calligraphic E and capital E, and the edges, the oriented and the non-oriented edges. And I assume that the rate are translational covariant, where tau x are the translation on the configuration, and tau x of local function age or function age on the configuration is the translation on the function age. Okay. So why can I go on? Okay. For a particle model, an exclusion process, we said, but okay, it's not necessary to restrict for what I have to say for an exclusion process, but keep in mind just because it's more simple. And the instantaneous current is defined as the difference between the rate of jump from x to y and minus the rate from y to x. And okay, I have this antisymmetric property that it means that the instantaneous current is a discrete vector field, or a discrete one form, if you want. What is known since long time is that when this current is gradient, namely I can decompose the instantaneous current as a gradient defined with the translation respect to a local function age, then I can write, as before, discrete hydrodynamics, where the discrete hydrodynamics is obtained by integrating by parts this discrete divergence of the instantaneous current, where the divergent instantaneous current is defined as the sum of the instantaneous current computed on the bond that are going out from the site X. Okay, in this case, if I observe the evolution of the empirical measure, the dynamics that you can prove for the empirical measure is that the empirical measure follows a diffusive PDE, where the diffusion is along a current J of rho that is given by the Fick's law, where D of rho is a positive symmetric matrix. Okay. The new result that I already presented in some talk some months ago was that I can, for example, in 2 dimension, I can construct a model where I have part of let's say, the rating 5 is decomposed in, let's say, gradient rate, in the sense that the difference between if I define the current for just this part will be this gradient term, computed with the translation on the edge. Here I'm always talking about nearest neighbor jump, okay? And then I can define a second part of the rate in the following way, where the current takes the form that I see in 6, that now I'm going to explain, where let's say this is will represent a discrete curl, where the translation on a face F is a face, like here in the picture, and a face can be oriented anti-clockwise or clockwise. When I denote the translation on a face, this is the translation respect to this point that zeta that I can associate for each face. And when I look at the bond xy, tau f plus of xy is the phase, such that with the anti-clockwise orientation, this edge belongs to the face, while f minus of xy is the unique phase, such that the bond xy belongs to the phase f minus, but with the clockwise orientation. So both A and G are local. Okay, now I'm not giving some example of construction of this model because I have to say other things later. But okay, this you can construct model with A and G are local, and then you can prove, you find some invariant measure for this model. You can find explicitly some invariant measure parameterized by density rho. The important remark is to note that, okay, here the current is decomposed. Okay, in this I use this notation because really this has an interpretation related to differential geometry and object decomposition, where this is a gradient part and this is let's say a discrete curl. Indeed, if we take the divergence, we take the discrete divergence of the current in a point X that I defined in the previous slide, I have that the divergence, it will be equal to just the divergence of J nabla. While the part J delta or eta is divergence free, and so the hydrodynamics of before here will be unchanged for the empirical measure. I will not observe in the equation of rho this part of the current. But what one can prove is that the macroscopic current that the macroscopic current that has to be defined as an empirical current follows in the hydrodynamic sense, so in a probabilistic sense, follows a generalized fixed law where I have a gradient part of this current plus an orthogonal gradient part that expressed in terms of metrics. This means that the diffusion of this kind of model will not happen along the usual fixed law, but will happen along a non-symmetric matrix, positive non-symmetric matrix. And indeed, when I take the divergence of this current, the diffusion for the density rho will be given just by this term. Okay, and okay, these two okay, this is nabla with the perpendicular symbol is what is called the orthogonal gradient. And YD of rho, A of rho will be, let's say, will be obtained as a replacement lemma in the function G and H respect to the stationary measure. Okay, now let me to tell you something about the transform maths in a model with vorticity. So I'm talking about vorticity since we have these microscopic vortices that will produce some macroscopic vortices in the current. And but of course, in the hydrodynamics of the density, I will be not able to see them. Okay, now I want to consider a continuous vector field on the continuous toroid, and I define with Gn its discretization. So this will be of order 1 over n, the contribution of this discrete vector field Gn of xy. And then I perturb the rates in the following way, such that okay, it's the jump can increase or decrease along the sign of the external field. Then I will recall you the Einstein relation, where they relate the transport coefficients for diffusive of a diffusive model, where sigma rho is the mobility, f of rho is the free energy density that one finds computing the large deviation function for the stationary measure rho, nu rho, and d of rho is the diffusion coefficient. So this is okay, the Einstein relation that are expected to be respected in the diffusive model. Okay. For this kind of model with vorticity, when we add the external field, we find that the current, okay, respect to the previous case, in the current it will appear an extra term where the mobility is proportional to the external field, and for this kind of model, what we find is that the sigma rho is given by Einstein relation. So the Einstein relation are verified, and rho t is the unique solution of the hydrodynamic 2, where okay, there is the hydrodynamic respect this current in Gj of rho. So here is missing a G. And so we show that the Einstein relation are verified for this kind of non-gradient model. In addition, the meaning of this result is that both the transport coefficient are related just to the gradient part of the current. And we think that this is a general fact for all diffusing non-gradient model, that only a part of the current will contribute to the transport coefficient of the hydrodynamics of the empirical measure. Okay, so let me just tell you quickly why this happens. So, the current for the perturbed model is given by the this expression 13, where I have the current without the external field plus this extra term proportional to the external field, the discretized external field. When I compute this, okay, insert the expression, I compute this second term, and okay, I find that is the sum of these two terms, where when I do a replacement lemma respect these two terms, the first will give me, okay, here is an example of an exclusion of this, okay, it's just a case, but okay, when I compute the replacement lemma respect to this first term, I will get the mobility. Here is, okay, let's say that there is an example where the mobility is the one of symmetric simple exclusion process. While the second term in the parenthesis 14, assuming a replacement lemma respect to the measured new rho, it will be always 0, independently from the intensity of the external field. So I conclude that the proof shows that the part of the dynamics with vorticity doesn't contribute to transport of mass. So we can say that at least in diffusive model with the vorticity, the mass is not transported by the vortices. And the proof, I let you know that the proof is not related to the intensity. The intensity of the external field, even if here we are using a weakly external field, is not, this fact that the vortices are not transporting mass is not really related to the intensity of the external field. So what we conjecture is that a symmetric model that are obtained as a strong limit of the vorticity part in the formula 9. That was okay. Okay, so I want to separate, okay, the rate here. The rate here I will have the gradient part and the part related to the function g. I want to do some kind of more or less stronger symmetric limit just for the part related to g. Then I will have still a diffuse model, even if in this case the vorticity part will be not divergence free. Okay.
Okay, thank you, Leonardo. Is there any question?
But question, what is the simplest model that you have in mind? Can you give us the simplest model where this stuff happens? Simplest one, not.
Yes, I should write, I should do some picture.
For explaining what happens in the.
Yes, it's okay. Let's say that okay, with here in the part in the rate 5 as in C age, you can take the rate of a symmetric simple exclusion process, and then in this other part you have to construct a function g such that, let's say, the jump along a direction, for example, a jump from this vertex to this other vertex, so in direction e to the y, will depend on the configuration of what happened on this edge and this other edge. So the rate will have the interpretation that when a particle jump will rotate along a face anti-clockwise or clockwise. And the function g now, yeah, by word, I should, yeah, it's why I should do a picture or give you the
Okay,
function.
so
But
practically
the thing is that
understood.
you have
Understood
dependence
the point.
on what is happening on the edge above, let's say.
Okay.
Okay. Can you think of a real situation where you can test this law, the fixed law?
In experiment,
Yes. I know you like this sort of questions because
yeah, I don't know. Yeah, I would be curious to. Yeah, honestly, I don't know how physics test the fixed law. I don't know. You can see maybe. Yeah, I don't know, because I was thinking smoke in a room, but the smoke, of course, will be more described by it will be not only diffusive. You will have also some transport term, I think, for. I don't know if the diffusion of smoke can be described by a kind of this generalized fixed law, but yeah, this is a question that yeah, I was asking myself, but I was looking the web, just internet, and the fixed law, they will describe the fixed law with the symmetric positive matrix. But let's say in principle it should be verified by a system that is evolving in a diffusive way, and let's say that in general, okay, in general, any in 2 dimension, in dimension higher than 1, gradient model are almost impossible to find. So this will be the typical picture of what happens in diffusive model in dimension higher than 1. Yeah, so it should be the typical. It should be the real law for any diffusive model, and for any model, for any realistic model that is diffusive, and yeah. So in principle, I don't know how to test the equation honestly, but it should be what is more the normal the equation where the metric is only a positive symmetric metric. It should be an exception, not the things that is more common. Since
but it contradicts a bit the fact that any real situation is actually in dimension higher than 1. So
yeah, in a real situation is dimension higher than 1. No, what I was saying that I would say that in interacting particle model in dimension higher than 1, the gradient system are really almost impossible to find. So I was wanted to say that at least this should be the typical diffusion for a non-gradient model in dimension higher than 1.
okay, so it should be observed quite easily. There is a question. A question for Leonardo. Do you see the effect of verticity as fluctuation and/or LDP level for the empirical density fields?
Allora, the fluctuation, yeah, for the fluctuation, I don't know. For the honestly, yeah, the fluctuation of the current, I don't know exactly how to study. Since honestly, at the moment I didn't find paper about fluctuation of the current. The empirical current, I didn't find fluctuation paper. About the large deviation, yes, you have to study the joint large deviation, for joint, the joint fluctuation of density current. And then there, yes, this part will contribute in the I didn't work on that, but they will. You will see they will. The dynamic related to the vortex will give a contribution to the large deviation functional of the joint large deviation for when I go to look at the joint large deviation.
Okay. Okay, thank you. Now I will ask you to stop sharing the screen so that Patrick.
Let me see how to do this.
Perfect. Already. Okay. So now we welcome Patrick Ferrari from University of Bonn, who will talk about local universality of the time-time covariance for the last passed calculation with generic initial profile. Please.
Okay. Thank you. So what I will speak is what Alessandra mentioned. We will give two results, one obtained with Alessandra and one with Ofer. So the setup is the last passage percolation, point to point, and then I will do also point to line. But so start defining the point to point. So for any point ij in the lattice in Z2, so ij in Z2, you define the random variable exponential distributed with parameter 1. Everything is independent. For an endpoint Mn, you can choose any path from the origin to the Mn that goes to the right or up. So this will be upright path. And then you define the last passage time to be the maximum over all possible upright paths. And for each upright path, you sum up the randomness that you see. The sum of the omega ij that you see along the path, this will be kind of the length of the path. So this is the random quantity that we are interested in. And the point to line, in case also with weight, this generalization consists that to take the initial point of the polymer or this path, upright path, this initial path to start from the anti-diagonal L. Moreover, when we speak about weight, means that on top of it, we put some random variable on the L, which is, they don't have to be independent anymore, but they are independent from the bulk. So the path P, which satisfy the equality, remind that this is given by the maximum over all this LP sum, all the sum. So the path P, which satisfy the maximization property, they are called the geodesic. And since we have continuous random variable, we have almost surely uniquely geodesic. And we also know the stationary model is easy to get by putting the randomness on the anti-diagonal to be a random walk with a given, not a simple random walk, but a random walk given by a difference. One step is a different two independent exponential distributed random variable. So the relation with the stochastic growth model, so that one sees that is related to a KPZ word, is that you can choose this line to be the space and this line to be the time. So if x is m minus n and t is m plus n, then one can define the height function at position x and time t to be just the LP, the last passage time to the point mn with this relation. So in particularly, when t equal to 0 means that you start on the line here, you have only the omega x minus x, which means the process that you put on the line is just the height function at time 0. And one important property is that this LPP satisfies the maximization. This satisfy this relation. So if you want to know the LPP to an endpoint here, you look what the LPP from the two neighboring point m-1 n and mn minus 1. You look which one is the maximum, and then you add the random variable in the last point. These will use a concatenation property. Now the question now is how to scale space and time to see something that is non-trivial. First of all, on a macroscopic point of view, which means on a law of large number point of view. So if you look at x of order xi times n, xn, and t also linearly scaled, so to be tau times n, then you look at the LPP, and this will be also of order n, so you divide by n, and this in the limit when n goes to infinity will be a deterministic limit shape. So the scaling, for simplicity, I do the scaling around the position x equal to 0, is the following. So in time, so there will be non-trivial correlation of macroscopic order, while in space, you have to move the non-trivial correlation are only on the order n to the 2/3. This means that this is how you have to scale. You look by this relation, you look at the point at time tau n, and then especially you move away of order un to the 2/3. This is just the correction from the law of large number approximation. And the point is that you have, in order to see a non-trivial limit, you have to divide by n to the 1/3. So for the central limit theorem, you would divide by square root of n to the 1/2, but here's the system is much more complicated. So this n to the 1/3 and n to the 2/3 are typical for KPZ universality class. So this, it was already known since a long time that if you take for a fixed time, so without loss of generality, take a time at distance n, which means macroscopically 1. So if you look at the process along at a fixed time, this will convert to some non-trivial limit process, some so-called RE2 process that is a stationary non-Markovian process, and RE1 process that is also stationary. So stationary process, and RE stat for the case where you have a Brownian motion initial condition here. The only important property is to know that this RE stat has increment that are two-sided Brownian motion because it corresponds to the stationary initial condition. So the first result, the main result of the paper with Alessandra, is not the only one, but say the one I want to present, is the following. So we look at the rescaled LPP, say along the diagonal at macroscopic time tau. So this we call key of tau. And if you look the same quantity, but at a position where we'll go away from the diagonal by order n to the 2/3 by parameter u, this will put explicitly the u parameter. This is coming in the formula. So the first result is that we have an exact formula for the stationary covariance for the point-to-point along the diagonal at time tau and at time 1. So key is the rescaled, limiting rescaled last passage percolation. And here we look at time, macroscopic time 1 and macroscopic time tau. So in the paper we have for different points, they don't have to be all on the diagonal, but here for the talk I prefer to specialize because the formula looks simpler. So here we see that this is as an exact formula. There is a prefactor multiplied by the variance of the key of 1. So and this is so-called Weierstrass distributed random variable. What is important here is that, okay, for this is an exact formula, but then one can ask, what can you do for the other case, not the stationary one? Say point to point, the simplest one that you have in mind. The point is that there you can also do something. And in particularly, if you look at the covariance, there is the first term, which is, I will explain what is coming, which is depending on the initial condition. For the point-to-point, this will be a GUE Trace-Williams distributed random variable. But important is that when tau is close to 1, the first order correction is proportional to 1 minus tau to the 2/3, exactly like here. But the term in front is exactly the variance of the stationary process. And then the next error term is at most order 1 minus tau. So this is a picture from a simulation of a previous paper with Herbert, where we had some conjecture, but we did not have mathematical proof. So this is just a so-called correlation because we normalized to be between 0 and 1, but otherwise you can think that it's just a covariance. The line is exactly the interpolating. So the formula is this formula here. And the point corresponds to the simulation for TASEP, for the total asymmetric simple exclusion process. For time t equal 1000 are the red one, and t 10,000 are the blue point. The matching is almost perfect. So where I wanted to mention where are coming the different terms. So the first step is to write the covariance of two random variables as linear combination of variances. This is a generic statement. You can put x and y to random variable, then you have x, y, x minus y. So this random variable is up to scaling the same as this one because there is the scaling limit in the same initial condition. So this is the reason while here you have the variance of P1, and this one will be the same except that there is a tau to the 2/3 in front. Now we want to understand where is coming this term. So K1 can be written as following. If you look at the maximizer, they at time tau n, maximizer to nn, at time tau n, they have to cross in somewhere this line. So, and if you take the limit, so the LPP to this point will be the maximum over all possible intersection point. The LPP from the line to here plus the LPP from here to here. So if you do the scaling and take n to infinity, you get to this relation where here will be just the rescale LPP to this point, and here is the point-to-point LPP. But for the point-to-point, we know that it's given by a stationary process and a process minus a parabola. And this factor 1 minus tau to the 2/3 and so are coming just because we look at a time frame here that is just of length 1 minus tau and not n. So which means here we look at K1 minus K of tau. So we have to just look at the difference. So since K of tau, it corresponds to K of 0 tau because it's the point on the diagonal. This is not depending on u, we can take inside the maximum. And now we have two independent objects here. Of course, there's still the maximum over these two independent processes. So first there is this one, and this is coming from this one. The RA2 process is stationary, so it's not a big deal. But then there is minus u squared divided by when tau is close to 1, is divided by a small factor. So you want the maximum. So in order to have the maximum, you rather don't want to have u very large, because if you say it's order 1, this object is like minus 1 over tau to the 4 over 3. So it's huge, but negative. So the maximum will not be there. So indeed, this factor will imply that the maximization process, the u that maximizes, so the argmax, is of order 1 minus tau to the 2/3. So one does the following. The first step, we do this change of variable. Instead of u, we can call this 1 minus tau to the 2/3 times b. And if I plug in, and here I add 1 minus tau to the 1/3, I plug in, I put in front, and I get this one. Now the second key ingredient is the following. Now v, the argmax in terms of v, will be taken over order 1. But then we have this process here. This is the scale height function at the time tau, macroscopic time tau, at a distance which, when tau is close to 1, as a small distance, 1 minus tau to the 2/3 is small. So we look just at the increment. And the idea was to use some idea going back originally to Cato and Pimentel, was to upper bound and lower bound the increment of the LPP through Brownian motion with slightly increased drift and slightly reduced drift. So essentially one shows that this object is at first order, essentially just a square root of 2 times a standard two-sided Brownian motion. And if you have to work a little bit, it's not a piece of cake, but in the end, you show that this variance is there is 1 minus tau to the 2/3, it's just this term to the square, times the variance of this term, and the error term we could estimate that are not larger than order 1 minus tau. And the point is that this formula is also key for the stationary, correspond to the bike range. It's known that this is just a representation, variational formula representation for the bike range distribution. So it's also not completely, it's not, so the fact that locally you get something which is related to the stationary one is not completely unreasonable, because you know that at least microscopically is very well known that the process converge to stationarity. Of course, here we are not macroscopically, we look on still on a large scale, but it's not so large. So in the end, it's still close enough to stationarity. So the second point I wanted to mention, the result was about the geodesic. I wanted to know if this fact that there is some universality close to the endpoint is reflected in the geodesic. The idea is the following. So what is the geodesic tree? To any point x, here say take on this line, for example, for instance, to any point x, you have a maximizer, a geodesic, px. If I write pp, not a point to point, if I put an L is the point to line, if I put a number or a row is the stationary one. So for any x, there is a geodesic, and the geodesic tree is just the union of all these geodesics. Now, what is important here is the notion of coalescing point. So if you have a point x and you look at, say, the geodesic ending in x, starting with the, say, flat initial condition or some random initial condition or the point to point, and the red one would be the geodesic with density 1/2. We call them Cp of PLX and P1/2 x this one is just the point where this geodesic start, they spread up. So until this point, after this point, they are identical because of uniqueness of the geodesic. So you cannot have some strange stuff, but eventually they will detach. They will be different, typically. Now, what we consider a cylinder. So the last point is n here. We consider a cylinder of width sigma n to the 2/3 and length 1 minus tau n. We want to think that tau is close to 1 and sigma is not too large. And the first result is the following. The detail, you don't have to read all this technical stuff at the beginning. What we first prove is that if you look the geodesic for the point to point, take any point in this cylinder, uniform, take any point that you want. And then you look at the point where the geodesic for the point to point problem on the density 1/2 problem, they coalesce. So we show that with high probability, this happens before the time L tau, that is the time horizon tau n. And this provided that tau is close to 1, like some delta, and the width of, if the width of this one, of the cylinder is delta n to the 2/3, the time should be close enough to 1, something like essentially delta to the 3/2. And then we have this bound that is uniformly for all large n. That in particular, if you think that take delta goes to 0. So if you look at a small o of n region length in time, then this will converge to 1. So this one is just the probability, as I said, that the geodesic, this should be as delta, that the geodesic will not cross. But this is for all points in the cylinder. This means that the full tree, starting from point in the cylinder, for the point to point and the random and the stationary one with density 1/2, the full geodesic tree will match with high probability. Okay. Now I wanted to give us a hint of how one had to do what we had to do. Essentially, first take any point x that is in the cylinder. So we can choose 2 points which are a bit farther, x1 and x2, which satisfy so that this point starts from a given region away from the origin, enough away from the origin, and they don't intersect the line that I call D1. So that is a bit larger than the original cylinder. And the same for x2. On top of it, for any geodesic starting in x, you also show that essentially they cannot cross D1 and D2. Of course, if you start close to here, they will enter in this region, but they will not go to D2. This implies, by the order of geodesic, that with some high probability, for all, not for one, but for all x in the cylinder, this will be, this green geodesic will be sandwiched between this one and this one. And this does imply that the green geodesic arrive in this region with high probability. And this simultaneously for all starting point here, not only one, but for all simultaneously. Now, if you know that this with a density is slightly larger than 1/2, start from this region, and the density slightly below 1/2, start from another region here, away from the center. On top of it, then we have just to see, the next point is to see that the point-to-point or the stationary with density 1/2 or the point-to-line geodesic will start in a region which is in between this A2 and A1. For the point-to-point is obvious because start from the region. For the other one, I have to prove. But essentially, this implies that this geodesic and this one will sandwich the two in between. Which means if we now are able to prove that the green and the blue geodesic until this time horizon are, after this time horizon are equal, then also these two will be equal because they are sandwiched between these two. And this is essentially what we have to do. We have to prove that this event where the green and the blue geodesic coalesce after the time horizon tau n occurs only with small probability. And with this are, of course, the proof is much more complicated, but these are the ingredients for the proof. Okay, I was a bit faster than expected, but it's fine. I think it's not a problem.
No problem. Okay. Is there any question from? I see that the audience is quite small now, but if you want to discuss a bit, we have some time.
At 6 o'clock in the evening, everyone is tired. I think.
I have one question, like about this result, last result you showed. So this high probability bound. So does it say at the end that this increments actually would decouple from like what happened before?
Correct.
I mean, since we have this high, yeah.
Here we. So what we essentially prove is that. So the increment, all the increment. So the geodesic to decide whether it goes to the right or going down, it depends on the increment of the LPP. So if it is more favorable to go in one or the other direction. And essentially here we see that in all this region, the increment as with high probability equal, which means the geodesic with slightly increased on decreased density will be the same. But afterwards, eventually they will detach because they come from different regions. I don't know if I understood correctly the answer. No, the question.
Yeah, I probably partly. I got your point. Yeah.
A question, Patrick. So what's the implication, if there is at all, of for like the Borges equations, like the solution? What's the so if you go away from this last passage, what's the idea of the geodesic coalescing? Is there like an interpretation in other models, under random growth models, the interpretation of being of the geodesic coalescing with the stationary one?
The geodesic itself, I see like if you look at, say, exclusion process or partially symmetric where you don't have the LPP, then you have to think what would replace the geodesic is essentially the space-time region where the information is flowing. So this would be the natural replacement of, so which means if you go to the left of the geodesic or to the right of the geodesic, if you do changes to the left or to the right, will not influence the evolution of a given particle precisely. want to make this exactly, it's not so easy, but the picture I have in mind is that instead of the maximizer, you have what I call the backward pass, and this is what gives you the information. So the correlation will really flow along this line. It's like the second-class particle in the total symmetric. We know that the geodesic, in some cases, correspond to one second-class particle in special cases.
This was for asymmetric cases, for asymmetric particle systems?
Totally symmetric. For totally symmetric, we know something.
But okay, but not for us.
In space-time picture, it should be similar, the situation.
It always confuses me, this connection between those polymers and the KPZ, the KPZ equation and all these. There's no relation. Is there like a? Okay, I have to learn a bit more about this. Yeah.
We will have time to discuss.
Yes, that's true.
There is also some time now, if you want. Go on.
Can I ask a question? Can I ask Fomit a question? So we didn't have time before. Do we have time for that?
Yes.
Yeah?
Until 6, you can go on.
So there's these, I don't remember now exactly, but I think there are these results by Zaytouni and what was his name? I forgot. About the corner, about like for random matrices where you look at the iterated, I think he did this, iterated low.
Fractional law.
For the OGE, I don't remember exactly. And there's another one by Basu and Ganguly and for the GUE, I think. So how is this related to your results there? Is there like and then is there like a universality of these exponents and the constants or?
Yeah, so the one that you're mentioning before, by Zaytouni and Paquet.
Elliot Paquet, yes.
So that was for this GUE that was like called fractional law of logarithm, because it's actually not 2 log, it's just 1 log. And that actually, I didn't get that much time to sort of stress on this. So what they did is that they sort of like took this, derived this for GUE, but essentially this is actually, if you try to interpret it in terms of Airy process or the KPZ, it's actually like giving a result for the fractional law of logarithm for the spatial process. What I did was I took this temporal process. For the spatial process, one would expect 1 log, like just log of t.
So what they did is they looked at the maximum of the.
So GUE, if you sort of like if you grow n, take the size of that.
For the GUE or which one there?
They took GUE, Gaussian unitary ensemble.
Okay, they took.
And if you take this n, the size of the matrix growing, and then derive something for the for this largest eigenvalue, that corresponds to actually the spatial process of the KPZ, or you can also think of it as a Airy process. Yes, spatial process.
Mm-hmm.
And so the reason why they had 1 log and we had 2 log is because the spatial process, the correlations decays faster, whereas in the temporal process, correlation decays slower.
Sure, yeah.
That's the main difference. So that's why I was thinking that one of the sort of interesting direction is for this KPZ class models, one can consider this for the spatial process. I can consider like this fractional law of logarithm, maybe for this in the H-take diamond case or any other case where this 2-point correlation function could be like at least analyzed. There is hope that one can find like similar laws. And on the other hand, for the KPZ, there is this iterated log, and that corresponds to again, like since I took this temporal process, I got this 2 logs. And the Basu Ganguly paper, they consider it for this last wave percolation. They had also 2 logs because their sort of way of looking at this process as also corresponds to like this temporal direction. So that's why they had 2 logs. But they were not able to like get this correct constant. The correct constant should be universal because like everything is converging to this Tracy-Widom GUE, so the constant should come from like this exponent or the constants of the tails from the Tracy-Widom GUE, but they somehow like were not able to sort of like correctly specify the constants.
I see. Okay, thanks. One more question, maybe. So, what you say where you have this spatial stuff, right? So, wouldn't that be that's Brownian? We know that it's like it's basically a Brownian motion with the measure
parabola.
Yeah, so with a change of measure, right? So it's absolutely continuous. So why wouldn't it be the same that like the Brownian? Why wouldn't have the same iterative?
Yeah, it's absolutely continuous with the Brownian, but not exactly. I mean, the Radon-Nikodym derivative would be weirdly behaving. So it's a locally
almost
Brownian
sure statement, no?
Sorry.
It's a normal sure statement. This
no, so you're looking at the process in a growing window.
Yeah.
Locally, it's Brownian, of course, but then since you're taking in a growing window, so overall behavior could be different from what you expect from the Brownian motion.
But almost surely the paths are that of a Brownian motion, right?
Yes, path locally is sort of absolutely continuous with this Brownian.
So even but like you said, you have a Radon-Nikodym derivative on a not locally, like on any compact interval, right?
Right, yeah. But then if you grow it, then it might be sort of blowing up. So that could be.
Thanks.
Anyone else wants to make a comment or? Okay. If not, I think we can close the session. So thank you all again for your contribution. Thank you, Patrick, Ofer, Tommy, and Leonardo. Yeah. Do you want to say anything? No.
I want to say thank you to
thank you, Sandra, and everyone for the organization.
Thank you. I hope this was interesting, and then you can also enjoy some other talks at the event. You can access with your password and username. Okay, if that's all, I will let you go to rest or to go on with your day according to your time zone. And okay, see you next time. Yep. And see you in Berkeley from it.
Yep, yes.
Bye-bye.
Bye-bye. Thank you.
Yeah, thank you.